very excited to have Alistair here. And his talk is entitled The Benefits and Hazards of Studying Mathematics. Alistair said that it's a talk about why he studies mathematics and why it frustrates him and why he lives in Green College. So I guess it's all interconnected. In case you don't know who Alastair is, or you might have missed my email, I shall present him to you. He is a human being on a giant spherical spaceship with no operating manual. He recently finished his master's degree here at UBC and is now pursuing his PhD. He is creeped out by the heat death of the universe and writing in third person. So join me in welcoming Alistair.
Hey, so this is my third year here at Green College, and I've always meant to do a member series, but I was like, no, I need to have something to present about. So having finished my master's, I was like, excellent, I can present on my master's thesis. Except, oh damn, the scrolly wheel is far too fast. So I thought about presenting on my master's thesis. Yes. Whatever. But then I was like, no, I don't want to present on my master's thesis. It's technical and the model isn't actually a very good reflection of reality. So I'm like, no, I won't present on the master's thesis. And I sat and I sat and I sat. And I had many very bad ideas. Yeah, so I had a large number of very poorly judged ideas on what I could do this presentation on. And so it ended up being solved, as one might expect here at Green College, as I was walking back from dinner and talking to Siriana and Anna, and ended up getting in a conversation. And from there I was like, yes, this is what I will do my talk on. So today I'm going to talk on the benefits and hazards of studying mathematics. Some of the things that I will talk about are very specific to mathematics. Several of the other things I will talk about are perhaps comments that may apply to academia in general, or perhaps not. That is for you guys to judge. Anything I say is only my own opinion, and may or may not reflect the opinions of other mathematicians, particularly pure mathematicians who perhaps have a different worldview to me. All the pictures in this presentation, bar one, are shamelessly pirated from the internet. So, let us begin. I'll do a very brief explanation of, wait, no, there's heaps of pictures in here that aren't pirated from the internet. Scratch that last comment about the pictures. Anyway, I'll start by explaining kind of what mathematics is, or at least how I view what it is. You guys probably have some idea, but, you know, my own perspective is kind of what this whole talk is about. So, what is mathematics? Basically, there are two things that you do in mathematics. Half of the time you spend building models, hopefully of the universe. The other half of the time you spend doing proofs, usually not in that order. So, let's say that there is something in the universe that you give a damn about. Let's say, for example, the Earth. You know, and you want to be able to say what is going to happen to the Earth next week, or next year, or next century, or sometime in the future. Or maybe you're trying to predict what happened in the past. Whatever, you want to know something about the Earth. So what you do is you draw a very, very, very careful, very accurate picture of the Earth. Like this. It's not quite a photo, but it's, you know, it's pretty close. So you try and draw a picture of it. And you draw it using equations. You go, these are mathematical relations. We know how diffusion works. So we're going to throw a little bit of diffusion into our picture right here. And we know how currents work. So we're going to throw a current, a flow into the picture just here where the clouds are moving around. And so you know how all the little bits of your picture work, and so you can make predictions using that. And if you're good, you end up with a picture like that thing over there, which is freaking fantastic. And you're like, this is the temperature of the ocean, this is how much salinity it has, this is where the currents are moving, and all that jazz. Now, there are, of course, several things that can go wrong with your picture. One of the main things that can go wrong is that your initial assumptions, your initial thoughts about how the world works could just be plain wrong. Like, you might just not know how the world works. You might just say things which are utter bullshit. The other thing that can happen is that you do know how the world works, but you suck at drawing. This picture is mine. I drew it this afternoon. Okay, and if you suck at drawing, no matter how well you understand the system, anything you do to try and represent that system is gonna come out all garbled and dumb. And you might not have the tools, so yeah, you can end up in a bit of a jam there. Yeah, okay, that's all I need to say there. So, your model can be done. This is the main thing that happens to first-year mathematicians, or first-year people who I am teaching in my life sciences classes, that they haven't actually learned how to draw within the lines yet, let alone draw the Mona Lisa. So, this is basically what we end up teaching people all throughout high school and early university, is how to actually stay within the lines and, you know, draw something that at least kind of makes sense. But it takes a long time before you graduate from using crayon to watercolor. Kind of, I'm stretching the metaphor a bit, but you can see where I'm going here. Okay, so the other thing you do in mathematics is you have a proof. Now, proof is basically kind of a mathematician's way of arguing this is how the paint works. We know you want to paint a picture, but if you don't know how the colors mix, you're going to have a bad day. So, proof is something like, I want to know how a triangle works. I've got a triangle, there's a right angle, I know how long a couple of the sides are, I'd really like to know how long the third side is. I mean, I could measure it, but if I'm building the Colosseum or something like that, I might not have built the Colosseum yet, so I might not be able to measure that. So you want to be able to say something about the future universe, something that has not yet been built. And so you need a theorem. If I was going to figure out this, what theorem would I be using? Yeah, this is Pythagoras' theorem. And so, but they came from somewhere. Some person sat down sometime a long, long time ago. I wish I could tell the story as more of a fable, but oh well. A long, long time ago, someone was sitting down and they came up with this theorem that said that the square of this side plus the square of the length of that side equals the square of the length of that side. And that came from somewhere. They had to come up with a very careful argument, and here is how they did it, or at least how I'm going to do it. Imagine you've got a yellow square. Your yellow square is a particular size. It's about a square meter, maybe. I don't know. And I'm going to draw some red triangles on my yellow square. And I'll label some areas. And I'm going to say that this area down here, I'll call that a squared, and I'll call this area b squared, and that kind of implies that the length of this is a, and the length of that is b. Yeah? That's all there is to it. Okay? And you'd agree that if I've got the same triangles on top of the same big yellow square, that the same amount of yellow is going to show through for me to see later on. So I'm going to rearrange those triangles. I'm just going to shuffle them around the square a little bit. Not actually going to do anything. They're the same size, they're the same shape. It's just like a jigsaw. I've shuffled a few of the pieces around. And I'm going to call that area that's left over c squared, which would kind of imply that the length of this is probably c. Okay? So if the amount of yellow that was on the square before is equal to the amount of yellow that was on that square afterwards, then we get that a squared plus b squared is c squared. It's a very simple argument. It's just a little picture. You can draw it. You could teach this to a 10-year-old, possibly someone younger. That's Pythagoras' theorem. This is one of the biggest underlying theorems of all of geometry, and it's how we measure distances between things in 3 dimensions, and it's a wonderful theorem. So, that was Pythagoras' theorem. That's proofs. Okay, I've covered doing models and doing proofs. So, basically, a mathematician's job is just to really, 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 really understand how this paint works. So if we're going to paint Earth, we've got a bit of blue, we've got a bit of green, we've got a bit of yellow. Not really sure what the white is for, to be honest. It's probably Antarctica. Whatever. They're obviously doing it wrong here because their canvas is white when really it should be on a black background, but we'll forgive them. They clearly look like they're at school or something. So, you want to understand how the paint works. You want to understand all these things. So today I'm going to tell you a story about what happens when you make bad assumptions. What happens when you think you know how the paint works, but you are wrong. So hypothetically, completely hypothetically, imagine that you are teaching for the first time in the mathematics department, and they give you office supplies. They give you pens and whiteboard markers and colored chalk. This is marvelous stuff. You can do anything with colored chalk. And you look around your room, which is a kind of whitish color, and you think, this room could be so much better if it was more colorful. So, but you want to make sure that the colors don't, cause trouble for you. So you make sure that they come off. So you go and you put the color on the wall. Perhaps you shouldn't have done that. Don't worry, it's been sorted, my best. Everything has been dealt with. I had assumed you'd already heard this story, actually. But perhaps I will be told off after this presentation. Oh well, too late now. So, you do it on a very small patch in the corner of the wall. With, green chalk. And you make sure it can be wiped off. You wipe it off. And it comes off beautifully. Okay. Good. So then the chalk, it's going to come off, right? I mean, everyone knows that chalk comes off walls. We just tested this assumption. We just made sure that chalk comes off. So we think that that's how the universe works, and we do things based on this assumption. And to be fair, the things were glorious and colorful and spruced up my room. I mean, hypothetically. For a certain number of months. Until I discovered something to my horror. My assumptions were wrong. The way I thought that paint works was not in fact the way that it works. The way I thought that differential equations work was not in fact how differential equations work. Purple chalk does not behave the same way as green chalk. It doesn't come off walls very easily. So, then you end up having to pay to have the room repainted. Which has been done, and the room is back in its original condition. So do not fear, everything has been put back to rights. I'm surprised this is the first time you've heard this. Oh well.
This is why I come on Monday night.
So anyway, as we have learned, I shouldn't have deleted those 3 slides that were in between. Oh well. As we have learned, if you think that the paint works in a particular way, if you think that the numbers add up in a particular way, if you think something and it doesn't actually work that way, you can run yourself into sometimes significant amounts of trouble. If you are an economist who is running all of the economy for an entire country, or the Reserve Bank or something, and you think that stochastic differential equations work the same way as continuous differential equations, and you run on that assumption, and then someone comes along like a couple years later and they're like, I don't think it works that way, man. It's different. And you go, crap, we've been running the economy the wrong way the whole time. And the same goes for radiocarbon dating or launching your spaceship or anything like that. So, this is kind of what mathematics is for and why I study it. Or rather, why it should be studied. That is not why I study it, though. I study it for the benefits, that to me personally. The main benefits being, it's a lot of fun. Once you get into it, once you actually understand what you're doing, it's fun, and you guys can give me the evil eye and say it's not fun, but it is. There's a system of rules. You know how the rules work. You know how things add together. It's a game. It's kind of like crazy ultra Sudoku designed by a drunken person who made the book, except half the problems don't have answers, and they don't tell you which one is which, so it's a little intense like that. Like, you can start a problem, you're working on it for 6 months, and then you're like, it just doesn't have an answer. There you go. But, whatever. So it's a lot of fun. It's reasonably objective. I really value this. I really value the fact that I could get into an argument with a tenured professor for a month, and by the end of it, they will just say, "Ah, yeah, you're right, I was wrong." And that's nice that you can actually just using words and stuff, and there's none of this jargon, and there's none of this having to look for evidence for 16 years, and there's... and it's reasonably objective. An undergrad could disprove the most certain professor, and that would happen, and the whole field would say, "Yes, you are wrong." And I assume this happens in other places. I hope this happens in other places. But it is much easier to say this is just completely wrong in mathematics than in a lot of other subjects, where you can argue, where there's rhetoric. Or at least that is the feeling I get. People may disagree with me. Okay, I'm not quite sure how Calvin and Hobbes represent objectivity. You get to feel clever. Has anyone here undertaken one of the treasure hunts I have set up? None of you. Ah, yes, okay, one, couple. Okay, and did any of you get really, really stuck on a question and you're like, "This is impossible, this is stupid, what was he thinking, this is the worst thing ever," and then solve it? When you solve it, no? No? Oh well, I'm sorry to hear that. But when you have been bashing your head against this wall, this isn't a wall, whatever. When you've been bashing your head against the wall for much, much time, you've been trying to solve it, and you've been trying to solve it, and then you do. And you know you're right. You know that this is the answer. That's a really good feeling. That is awesome. Also, other people seem to think you're clever too. That is not actually something I particularly value. It does perhaps improve your employment prospects, but that's not why I do it. And the fourth benefit, oh God, counting. The fourth benefit, and this is the one that I value above all the others, is that you get to switch subjects easily. You're not the best at any given subject. You really aren't. Well, except for mathematics, I guess. But you can switch so quickly, as in I have got to study so many different things since getting to UBC. There has been epidemiology, and then you can study the cells that happens, and then you can read papers on rivers, and then there's a guy in my office who studies fusion reactors, and then I did a course in meteorology in undergrad, and there's encryption, which is number theory, and I get to study evolution for research, and you can do the dynamics of plane wings and how the fluid flows around them and how this conspires to lift the plane, and you can talk to lecturers who have done some really quite disturbing studies on various electoral systems and the statistical anomalies which have been encountered during certain elections. So, you get to study a hell of a lot of things. I really love that. I really love switching subjects because I have a short attention span. I really don't have the attention span to last a 3-year PhD, so having the ability to switch between things is awesome. So, those are the benefits of mathematics. This talk is going way faster than I expected. Oh well. But I didn't just promise benefits. I also promised hazards. And so I am going to list the 4 things which kind of most freak me out and most worry me and most frustrate me about my field of study. And I hope this is not too much navel-gazing or too meta or whatever, but it's what I wanted to talk about. It is really easy to get distracted. Like, you can start building a model and it's not really a model of any particular thing, but you can start building it and it's this puzzle. You can solve it. If you just spend another 3 decades on it, then you'll be able to make an amazing contribution to stochastic differential probabilistic information theory. It'll be wonderful, just a few more decades. You can get so distracted so easily. It's easy to get arrogant. Like, you know things about other people's subjects that they don't. Like, I read economics papers and go, no, 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 that doesn't even make sense what you just wrote down. You're doing it all wrong. And so you see people doing things mathematically all wrong, and you start to get this idea that you could do it better. That if you were the one doing it, then everything would be okay. Which is, of course, a terrible thing to think. And it's a terrible thing to do, because just as they don't know certain things about mathematics, you don't know a hell of a lot about their subject. So anything you do is going to probably be 10 times more wrong. Maybe. I'm not always that sure, given some of the things I've read. But anyway, there's also the problem that when all you have is a hammer, it can be tempting to apply it to everything. Like, if you know calculus, then you're like, we'll just study Norwegian literature using calculus. That'll work fine, right? Right? I mean, there's the words, and they increase in frequency, and these ones decrease in frequency, and when this one goes up, this one goes down in response, and you can take the flow, and words will flow from place to place, as in that's how diffusion works, right? They're just particles? Or maybe not. Okay. But none of these are actually the most dangerous thing that I think could happen to a mathematician. Well, in mathematics. I'm not talking about getting shot or something. To me, the most dangerous thing that can happen is it's very easy to get cowardly. It is very easy to build a nice model that is kind of pretty, and you can solve a bunch of mathematics about it. It is very easy to build it up and add more details and stuff like that, and never ask the universe if you are wrong. It's very easy, because if you ask the universe whether or not you are wrong, the universe may come back to you, and it may say you're wrong. It may say you're stupid. It may say you didn't do anything right. It may say you don't know what you're talking about. And how can you publish that? It's very easy to sit down and do a few models and make a few nice publications and submit them to a nice journal and keep doing this and never ask if it means anything or not. And that scares me, because I could see myself doing that. I did. Like, I studied this epidemiology class, and at the end of the class, we got all this data from an ecologist who had been studying the western tent caterpillar. Have you seen these things about? They're kind of creepy, and they scale about, and they make these tents in trees, and they go together and keep themselves warm over the winter months, and their populations build up, and at some point you get huge, like heaps and heaps, millions of them taking out entire forests and stuff. And then this horrific plague comes along, and they dissolve into pink ooze. Like they do. This is what happens. And we had like 30 years of data on a bunch of islands, and we were asked to make a model of this. We had like a month to try and make a model, to try and say, if this is how many there are in this year, and this is how much the infected percentage is, can we predict how many you'll have the following year? And we spent a month or so working, probably a month, it was just a class project. We spent a month working on it, and we couldn't get it. Like, we just didn't. We couldn't. Like, it was too hard. There wasn't enough data. Time was short. Our understanding was flawed. I don't know. We just didn't get it. Maybe it was just too complicated. Maybe the universe is not as simple as we wished it was. But that doesn't mean we should study something that is simple. That means we should study the universe, even though it's hard. And so that, to me, is the scariest thing, is failing to study something that is actually real. So, that is a dour and dire note. So, let us continue. What are some solutions to this thing? How might we avoid, or we, the mathematicians, we, academia in general, we people, how do you avoid studying something that isn't real? How do you actually connect to the universe? And one fairly reasonable solution to me is you live at Green College. You have dinner with people who know things that you don't on a regular basis, and you ask them questions. God damn it. You sit there at dinner and go, what is your research about? Tell me, God damn it, tell me. Tell me those things you have been researching. Come to member series, learn something at member series, look up papers that someone gave you at member series. What else can you do? You can ask questions. If mathematics is this beautiful toolbox, it really is. It is an amazing toolbox, and you can study so many different things with it. I've just finished a course on industrial mathematics, where we studied fish populations and capacitors and explosions and children on swings and resonance in radios and trying to balance a pole on your hand while moving about and all these different things. And they're cool, but they're perhaps not the important things. Some of them are. The fish stocks was an important one to avoid stuff. So, I'm going to say, I study mathematics. It is a brilliant toolbox. If you are trying to study something, and if there are numbers in it that are giving you trouble, that are too nasty, come talk to me. I like collaborations. That is what we are here for. They built Green College because someone, sometime back in the past, maybe Cecil Green, I don't know, we should check our history books. Someone said this. They said that if we have a whole bunch of academics and we put them all intermingled, we will get more than 100 academics worth of research done. We won't get 100 academics worth of research done. We will get 200 or 300 or maybe only 100, but ultra-relevant research or something like that. I don't know what they said, but they thought that we could do better than we could do alone. Because I don't think we can make it alone. I don't think I can. I'm not wise enough. I don't know enough things. I can't learn quantum theory and political science and languages and everything. There's just too much stuff. And it's overwhelming and it freaks me out sometimes. And that's kind of all I got for now. It was a bit of a rant.